In this lesson, you will learn how to solve systems of equations using inverses of matrices. Now, before we can solve a system of equations, we first need to learn how do we find the inverse of a matrix. And even before that, what is the inverse of a matrix? Well, the inverse of a matrix, by definition, is a matrix that is multiplied to another matrix, which results in the identity matrix. So if you're given two square matrices, A and B, and if A times B equals B times A, which is equal to your identity matrix, then A and B are inverse matrices. Meaning if I multiply A times B or B times A and results in the identity matrix, then they must be inverse matrices. And the purpose of this, as we stated, is to solve systems of equations. Now, how do we find the inverse matrix? Well, let's say we have a matrix A, and in the matrix we have these four numbers. So with a 2 by 2 matrix, what we do is we are going to take 1 over the determinant of the matrix, and then we're going to switch A and D. We're going to switch the position, so now we have a D and an A, and then we're going to change the sign of the B and the C numbers. So whatever is in the top right and bottom left, we change the sign. If it's positive, make it negative. If it's negative, make it positive. And a little side note along the same lines is that if your determinant is equal to 0, then A can have no inverse, which makes sense based off the definition, because if we have 1 over the determinant A right here, this cannot equal 0 because then we have something that is undefined. So therefore, the determinant of the matrix must not equal 0. So here's an actual example with real numbers. So we're trying to find the inverse of matrix A. Well, to do that, as we said, we need to find 1 over the determinant of A first. So what is the determinant of this 2 by 2 matrix? Well, to do that, I take 3 times 2, and then take 3 times negative 1. So I have 6, and then minus 3 times negative 1 gives me a negative 3. I minus the negative, which gives me a positive 9. So now I have 1 over determinant A, which is 1 over 9. And then I have to switch these two numbers. So the 3 goes in the bottom right, and the 2 goes in the top left. And then I change the sign of these other two values, the 3 and negative 1. So the 3 becomes a negative 3, negative 1 becomes a positive 1. So then I multiply 1/9 by this matrix. So I get 1/9 times 2 times negative 3 times 1 and times 3 to get this resulting matrix. So this matrix right here would be the inverse matrix. Let's do another one where here we're trying to find the inverse of this matrix. So once again, we need to find the determinant of the matrix A. So to do that, I'm going to multiply negative 2 times 6 to get negative 12, and then subtract 4 times negative 1 to get negative 4. Well, when I subtract the negative 4, that gives me a plus 4, so negative 12 plus 4 gives me a negative 8. So I have 1 over the determinant of A, so I have 1 over negative 8, and then I switch the negative 2 and the 6, so now I have 6 and negative 2, and I change the sign of the 4 to be a negative 4, and then negative 1 becomes a positive 1. So then I multiply the negative 1/8 times each of the numbers inside of the matrix to get negative 6/8, which would be negative 3/4, positive 4/8, which can reduce to be 1/2, negative 1/8, and then a positive 2/8, which reduces to 1/4. So this would be my resulting matrix. Now, to show you that the matrix times the inverse would indeed give you the identity matrix back out, we're going to walk you through multiplying those two matrices. So here was the original matrix, and then this was your inverse matrix. Now when I multiply, we have a 2 by 2 multiplied by a 2 by 2 matrix. So you can multiply them together, and the resulting matrix would be also a 2 by 2. So now I'm going to multiply the first row by this first column. So I'm going to get negative 2 times negative 3/4 plus 4 times negative 1/8, and then I get 3/2 minus 1/2, which is going to be 1. So that goes in the top left corner. And then I do the same thing with the first row and second column. Multiply -2 times 1/2, and then the 4 times 1/4. You add those together, you get -1 plus 1, which would give me 0. So 0 would then go in the top right corner. Because I'm dealing with the first row, second column, it's going to go in the first row, second column. And then I need to multiply the first and second row by the second row for the first matrix. So first and second column multiply by the second row of the first matrix. So -3/4 times -1 gives me 3/4, and then 6 times -1/8 gives me another -3/4. So you subtract those, you get 0, and that goes in the bottom left corner. Then I multiply the second row by the second column. 1/2 times -1 plus 6 times 1/4 gives me -1/2 plus 6/4, which is plus 3/2, which would give you a 1. And that goes in the bottom right corner. So notice when I multiply the matrix by the inverse matrix, the resulting matrix would be the identity matrix. So as we see up here, that if we take a matrix A, multiply it by the inverse matrix, we're going to get back out the identity matrix. So the I means identity matrix, and then A to the negative first means simply that we have the inverse matrix. And now we can use the inverse matrix to solve systems of equations. And to prove that we can do this, here we're given two general equations, where we have ax plus by equals e, then cx plus dy equals f. And a, b, c, d, e, and f are all just numbers, and x and y are the variables. So what we can do to solve a system of equations is we can put the coefficients in one matrix. So the a, the b, c, and d put over here in one matrix, and then the variables put over here in another matrix. And the e and f go over here in their own matrix on the right side. So now instead of writing out each of these matrices, all with the different variables, what I want to do is make it a little simpler to work with. So we're going to let that first matrix be matrix A, we're going to let the second matrix be matrix X, and the third matrix we're going to let be matrix B. So what we have instead would be A times X equals B. And now assuming that the inverse matrix of A exists, then what I can do is multiply both sides by the same number or same value. So I can multiply both sides by the inverse matrix, because that's legal in algebra, as long as we do the same thing to both sides. And the order does make a difference, so we do need to make sure that when we're multiplying, that the inverse matrix will be on the same side that you're multiplying by. Meaning the inverse matrix is on the left side when you multiply by A times X, and therefore the inverse matrix on the right side also needs to be on the left of matrix B when I multiply. So now we can use the associative property and we can group together the inverse matrix with matrix A on the left side. And we just showed you that the inverse matrix multiplied by the original matrix will always equal the identity matrix. So we can replace this right here with the letter I for identity matrix. And we also know that the identity matrix times any other matrix will not change the identity of the original matrix. So if I have the identity times X, I will still have X left over. So I have just solved for X. I have solved for my variables right here. We let X and Y equal X. So we've solved for your unknown values by using inverse matrices. Now let's take a look at an actual example with real numbers. So here we have two equations, and I want to begin by making a matrix out of the coefficients 3, -4, 2, and 5. So we're going to make a matrix over here, and then your variables x and y make a second matrix with those, and the 6 and 10 on the right side of the equations make a matrix out of those as well. And so this would be matrix A, this would be matrix X, and then on the right side would be matrix B. And now from what we just showed you, what we want to do is to solve for matrix X, we're going to take the inverse of matrix A and multiply it by matrix B. So to do that, we need to find the inverse of matrix A first. And the inverse of matrix A we find by taking 1 over the determinant of the matrix, and then changing the 5 and the 3 around, and then changing the signs of the -4 and the +2. So then to find the determinant, we take 3 times 5 to get 15, and then 2 times -4 to get -8. So now I have 15, and then I subtract the -8. So 15 minus -8 would give you a +23. So then I multiply 1/23 times this matrix to now get 5/23, 4/23, -2/23, and 3/23. So then what I do is I take the inverse matrix of A, multiply it by matrix B, and when I do that, I'm going to multiply the first row by the first column. So the 5/23 multiply it by the 6, then multiply the 4/23 by 10. So what I have is 5/23 times 6 gives me 30/23, and then 10 times 4/23 gives me a 40/23. And then I add those together. And then same thing for the second row right here. I take 6 times -2/23 to get -12/23, and then 10 times 3/23 to get 30/23. Then I add those two together as well. So for X, for the top one, we get 70/23, and for the bottom, we get a 18/23. So what I've done is I've solved for X and Y. X would be 70/23, and Y is 18/23. And that is how you solve a system of equations using inverse matrices. Now we're going to learn how to solve matrix equations using the same kind of ideas that we use for solving a system of equations. So here we're given this matrix equation, and the objective is to solve for X. Well, to solve for X, I need to get X by itself. So let's get rid of this subtracted matrix right here. So to get rid of the subtraction, I need to do the opposite, which is addition. So I'm going to add that matrix to both sides. So now I'm adding the matrix to both sides here and here. So now this will cancel. And on the right side, I have 2 plus 1 to get 3, 1 plus 2 to get 3, -1 plus -3 is -4, and 3 plus 4 is 7. Now to finish this off, I need to get rid of this matrix in front of the X. So what we have is a matrix times X, and to get rid of this matrix, I need to multiply by the inverse matrix. So I'm going to multiply both sides of the equation by the inverse matrix. And that's what you see right here in yellow. Now when I multiply the left side by the inverse matrix times the original matrix would give you the identity matrix, which would not really change anything. Essentially, you're just canceling these out when you multiply by the inverse matrix. And on the right side, I just need to figure out what is the inverse matrix, then multiply by the red matrix. So to find the inverse matrix, what I do is I begin by taking the determinant. So the determinant is 5 times 2, so 10, then minus 3 times 3, which gives me 9. So 10 minus 9 would give me 1. And so what I do is I take 1 over the determinant. So 1 over 1. I then change the 2 and the 5 around. So now I have 2 there and a 5 in the bottom right. And then I change the sign of the 3 and the 3 to get -3 and -3. So what I have is the inverse matrix equals 2, -3, -3, 5, which I multiply by this other matrix over here, 3, -4, 3, and 7. So now when I multiply, I take the first row times the first column, so 3 times 2, plus -3 times -4. That's going to be for the top left. For the top right, I have the first row by the first column here, so 3 times 2, plus -3 times 7. And then I'm going to do the same thing now with the second row. So second row, first column, I have 3 times -3, and then -4 times 5. And then second row, second column, I get 3 times -3, plus 5 times 7. So when you add and multiply all of these, my resulting matrix would be 18, negative 15, negative 29, and a positive 26. So that is how you solve a matrix equation by using addition, subtraction, and then finishing it off with using the inverse matrix. And that concludes our lesson for today. We will see you next time.